Good afternoon, ladies and gentlemen. Thank you all so much for joining us today. On behalf of AUVSI, I am very pleased to welcome you to today's webinar, Designing to Scale, Validation and Verification from Concept to Deployment. My name is Shannon Walker, and I am a program manager here at AUVSI and will be your host for today's webinar. Before we get started, as many of you know, we have a few housekeeping items that we always like to go over. So all of the participant lines will remain muted throughout the broadcast. A recording of this webinar is in progress, and it will be emailed out to all attendees along with a copy of the slide deck and posted to auvsi.org within the next week. If you are listening to the webinar today and you need any assistance, please send a note to the webinar leader using the chat box on the right side of your screen. If you don't see that chat box, click that little chat bubble icon that can be found at the bottom right-hand side of the screen, and that should open up the chat box panel. Please note that any links featured in the slides today will also get shared through the chat during the presentation. So after the presentation, we're going to open up the session for Q&A. So attendees, you are always encouraged to submit your questions at any time throughout the webinar using the Q&A box on the right side of your screen. But the questions are going to be saved to be answered towards the end of the presentation. And another important thing to note, this is a different box from the chat. So just make sure you're submitting all of your content questions for our speakers using that Q&A panel, which can be found directly underneath the chat panel. One other quick note for attendees, you can change your screen view by clicking the layout icon, which is found in the upper right-hand corner of the slide screen. So for example, if you only want to see our active speakers, you can deselect the option that says Show Participants Without Video. So go ahead and play around and find the view that works the best for you. All right, let's get started. We would very much like to thank our sponsor today, United Electronic Industries, for their generous support. For anyone who may not know, United Electronic Industries, or UEI, is a leading developer of control, test, monitoring, and verification validation solutions for UAVs and UASs. UEI's flexible systems feature interchangeable chassis and a range of I/O options, providing the maximum potential for design reuse. All of UEI's hardware is backed by a 10-year availability guarantee and 3 to 5 year hardware warranty. So we are excited to have an excellent speaker with us, part of the UEI team, Mr. Eric Gothert, the Senior Director of Business Development and Strategic Marketing. So at UEI, Mr. Gothert has designed, managed, and implemented projects that collect real-world data for aerospace, energy, and defense industries, so they can build smart systems that are reliable, flexible, and rugged. He has more than 30 years of experience in industry-wide hardware, software, and I/O application solutions. He also has an engineering degree from Cornell University, so we are all very clearly in good hands today. And with that, Eric, I will hand it over to you.
Thank you, Shannon. I certainly appreciate it. And thank you, everybody, for attending and giving us your time today. What we will be talking about is design to scale, how to work your systems from concept all the way to the final flying solution. And in the meantime, I'm actually going to turn off my camera because I tend to get up and walk around and gesture. And the way these cameras work is you'd be looking at my belt or my belly button. So that wouldn't be so good. So off we go. So this is just a quick overview of what we're going to talk about today. Hopefully everybody is familiar with the V model for verification. We're going to look at where you are in that V model, the tasks that you are doing. They can be all virtual or a mix between real and virtual or all real. And then we're going to hopefully help you ensure that your system can scale up and down so that you can reach safety certification and time to market, which are not necessarily mutually inclusive things. We will present methods of code and hardware reuse to accelerate the development and deployment of your autonomous flight or mission controllers. So this is a quick overview. We're going to look at some of the context and challenges around this. We're going to look at why standardize on a system. We're going to look at very specifically the Vistas protocol, or ED247. If you haven't heard of it, you will hear of it now. And we are going to figure out why it works. And then, of course, have questions and answers at the end. So hopefully everybody is familiar with the V development model to set the stage. Whether you are in software development, hardware development, or systems, this is entirely applicable as a model to show how each phase can influence the next, as well as all the way to deployment. Typically in our world, the closer you are to the left side of the V, there is more simulation to prove out the concepts, while the right side of the V is real hardware to be validated against those requirements and the models. Oh, and of course, I can't forget all of this is moving towards certification. So we can pull out the various simulation and testing needs along the way, starting with 100% simulation. Typically, the system or unit is simulated using a CAD or computer-aided design tool to prove out the concept. As we get into the more detailed design, more unit testing and component testing is needed. Some of the supporting signals or systems will still need to be simulated. Many times, this is on a single test bench. Moving back up the right side of the V, after a component is identified as a good candidate, hardware in the loop testing is done for integration testing. More of the other components are real. However, some are still simulated. This is done perhaps in a system integration lab or on a hybrid test bench. The candidate passes the validation criteria. Sometimes it will be integrated in a full fidelity simulator so a pilot can, quote, fly it. Of course, it's better to test this on the ground than in the air at this stage. Eventually, there is testing on the vehicle in real-world conditions with instrumentation, of course. There is ample opportunity in this design pattern to reuse models, code, and hardware. Is this opportunity lost at your company? Let's look at a couple of the challenges. Well, as you know, in every organization that I've ever seen, there's pressure on the test cost and cycle time. And so it starts becoming very, very mandatory to reduce that cost and delay of the link between the bench and the realization and the validation itself of the hardware. You need to secure the in-time availability of the ground test resources, typically months or even many, many months before flight. You need to find a way to reuse and share more efficiently hardware and software resources. Test and especially integrate as early and often as possible in the development cycle, hoping to improve your efficiency of the test process. And then, of course, what you'd like to do is take and benefit of new technologies like extended enterprise and cloud computing. And nowadays, especially during the COVID-19 crisis, you want to do all this remotely or as remotely as possible. And this is also driven by the fact that many of the components are not necessarily co-located with your integration and test benches. And then, of course, comes the impact of obsolescence and now some of the supply chain challenges that we are seeing, which are unfortunately occurring more and more frequently. Hopefully, this resonates with you. Hopefully, you have seen some of these challenges. Other challenges specific to the bench itself is that they're typically based on proprietary solutions. Often that the control and display software is the result of internal software teams. Those same software teams are writing this code when they should be trying to validate the designs. Typically, many of the hardware vendors have proprietary interface, and many times these drivers are only available for a limited number of operating systems or CAD tool type systems. And then the development and maintenance of dealing with these obsolete or difficult to find parts in these systems is becoming much more costly, and it wasn't obvious in the very beginning anyway. I certainly did not see this supply chain crisis coming. So for the integration benches themselves, the resources needed are most of the time dedicated and co-located in the same area. Well, this means that typically they're in a centralized acquisition bay, which implies complex and expensive wiring to get it all working. Switching to and from a virtual component or a simulation to a real one is not easy and is not obvious. And of course, if you are using a simulation or a virtualization versus the real equipment, you would need to design the test scenarios twice, as well as figure out how to monitor each. And despite some of these improvements, silos are still existing between simulation and test. So hopefully what you're going to see, virtual testing is only going to increase. So why should we standardize an approach to solve these issues? The major goal being the reduction of cost, of course, and by minimizing the development and validation effort of these systems. Using many vendors of instruments, if they standardize, then it's up to the vendor to simulate. There's a large choice of hardware you can use. Many times they are complementary of each other, and it certainly helps with some of the obsolescence mitigation. On the vendor side, there's many buyers of their systems because if everybody's using the same standard, then there's interoperability between entities, as well as there is the scaling effect of the cost of having multiple people buying your equipment. One of the big things are they always say many minds are better than one. If there's more eyes on the standard, then we can reduce some of the risk. We can reduce some of the cost because there's more than one person maintaining it. Hopefully there is some robustness in the architecture, again, using all these different eyes. Hopefully there's a bunch of innovative ideas. Again, many brains on one problem. And then getting down into the software side, there's the abstraction layer associated with the standardization. So it can reduce some of the developmental efforts if you use some of these abstraction layers. It makes it compatible with many different kinds of OSs and many different kinds of hardware. You can standardize on a common language, and of course, hopefully, you can reduce your learning curve. If we were to put this in a nutshell, with many vendors of instruments all agreeing on a common driver or hardware abstraction layer, all working together with the final customers and integrators, a better system can be developed. Well, this is where I'd like to introduce you to something called Vistas, or the ED247 standard. This standard is defined by EuroCai, which is the European organizational leader in the development of worldwide industry standards for aviation. This standard, called Vistas, means or stands for the Virtual Interoperable Simulation for Tests of Avionics Systems. Its objective is to define a common standard so that virtual component models can be shared between the different aeronautic industry actors during the whole product lifecycle. For example, from full simulation of a concept or a controller to the hybrid test benches mixing real and virtual components, as well as the simulators delivered to the aircraft end user for training. One of the main aspects addressed by this standard is the virtualization of the analog, discrete, and avionic buses. This virtualization is done by digitizing and multiplexing the information on an Ethernet bus, ensuring that the timing of the signals is preserved. Remember that, the last point is key, that the timing of the signals need to be preserved. So, I mean, kind of obvious, the main objective of this standard is to improve the integration test process by reducing drastically the associated costs and delays, and starting the process as soon as possible during the development cycle. You're going to start with those virtual models or the simulations. So to achieve this, the standard proposes to share models between the different actors easily, to use these models in the frame of full simulations or hybrid ones, mixing real and virtual components that don't necessarily need to be co-located, and virtualize the communication exchanges between the different elements on the IT network. Well, these lofty goals are shared by these companies that currently have team members around the ED 247 working group table. They represent some of the biggest names in the aerospace and aero engines companies around the world. And there are a good number of key instrumentation and data acquisition system suppliers in the list as well. As we mentioned previously, that the main aspects addressed by this standard are the virtualization of the analog, discrete, and avionic buses. This virtualization is done by digitizing and multiplexing the signals onto an Ethernet bus, ensuring that the timing of the signals is preserved. We need to ensure to minimize the introduced latency by limiting the CPU, memory, and bandwidth usage so we can reproduce the original signal with a high accuracy in magnitude and timing. So why are we calling it virtualization? First of all, instead of discrete analog and the wiring harnesses associated with them, it is all carried on the Ethernet line of an IT network. Oh, good, I've crossed out the wired. It's on an IT network. The data can be from real instruments or just a data packet from a model. The receiver would never know. Here's the basic transport protocol used as an Ethernet UDP packet. We'll be reviewing this in detail a little later in the presentation. So let's look at a high-level architecture of Vistas. You can see that everything is based on this Ethernet bus with many different components connected to it, from virtual to real to various loads and various tools. So let's review. There are the real components, real avionics, sensors, and the like. They need something called an I/O bridge to convert the signals to a Vistas packet and back. This is where the discrete wiring happens. There are virtual components that generate Vistas packets directly. These are software simulations of any component and can receive a Vistas packet to modify their behaviors. And of course, the tools. These are components that include recorders, playback devices, display tools, air injection tools, and the like. Each either consumes or generates the Vistas packets. So the backbone is the Vistas packet traveling over the Ethernet network, which can be generated and or consumed by anything. The receiver does not know if it was generated by a real device or a simulation. It's just a UDP packet. This virtualization makes it 100% usable on both sides of that V development cycle. From full simulation on a single computer or multiple computers simulating many different devices, or even a full-on cloud computing solution. For more concrete or physical device testing, Vistas is great at unit testing where all the inputs into the system are not present and are typically simulated, as well as for integration testing with more physical and less simulation to even the training simulator. In fact, models can be reused from the beginning to the end of the development chain and even into maintenance. Here's an example of a test bench that has various devices. Let's call them A, B, and C. They are interconnected via an Ethernet cable. Any signal routing is accomplished through the software configuration. All the parameters are easily displayed on the display tool. It certainly makes the bench design and infrastructure much more simple and generic. And it is easy to substitute a piece of real equipment with the simulated node. After all, it's just UDP packets writing on the Ethernet bus. Another design pattern is the replay and analysis of information gained in flight. The data is acquired and either saved directly into the Vistas format or with a converter node. The dataset can be then replayed onto the same display node, as well as replayed onto avionics and controllers with the I/O bridge. Whether that dataset was modified from the original for air injection, replayed more slowly, or just played as is, it is entirely up to the user. Let's take this even further. In this time of a global pandemic and the fact that the various components associated with a system may be designed and manufactured all over the world, virtual testing of the system can not only save you money and time, but will certainly help stop the spread of this virus called COVID. The distance between the equipment is not limited by the analog wiring anymore. Everything is over Ethernet now. The components can be in different rooms or different buildings at the same site, at different sites, or even still at the OEM. This can allow earlier integration testing, earlier validation, earlier anomaly detection, and shorter design cycles. All this is brought out by the virtualization of the data. When looking at the traffic around the bus, Vistas uses a concept of channels. Each channel is a data set sampled at the same frequency, whether analog or digital or a mix of both. Message-based buses such as CAN or ARINC 825, ARINC 429, Serial, Ethernet, and the like are also supported. For each type of channel, the structure of the data packet is defined by Vistas, as well as how the data is packetized. Each channel is associated with a communication interface, currently a UDP socket. But of course, and we will see that there is room for expansion on this. Here's an example of a data packet, both of a single channel and multi-channel data. Mandatory fields are the actual data, with optional ones including timestamps and transport streams. So let's review. The ED247 standard provides an ultralight way to virtualize the exchanges between real and virtual components. It provides the capability to log and replay the exchanges between equipment with accurate timing. And it provides an I/O hardware abstraction layer, making the software independent of that hardware. So these capabilities allow the sharing and reuse of the models all along the different development phases. For example, the reuse of the models for the development of the end user simulators with a minimal amount of work. It allows efficient hybrid testing where we can mix real and virtual components and easily swap between real and virtual components on a bench. It allows the realization of distributed testing with the involved components not necessarily co-located in the same building, site, or even the same continent. Earlier integration testing, even with some of the components still located at the provider facilities, and with the wiring reduction and simplification, there will be a drastic cost reduction of the bench design and implementation. All this because we can virtualize the information. One part that we haven't discussed is the resolver concept in the ECIC file. This file takes into account all of the components and the network information, ensuring that the data is routed where it is needed. It will point out conflicts and missing sources, making for a smooth implementation. It is the key when thousands of signals are involved. The I/O bridge configuration mechanism is pretty simple and based on two XML files. The first one, based on the ECIC format specified in the ED247 standard, contains all the information relative to the network aspects, the IP address, the port number, the structure of the data packets, while the second one is based on a pre-existing format XIDML file describing the hardware configuration of the I/O bridge, For instance, the input wiring, the output wiring, the gain, the filtering characteristics, and the type of channels. These two files are used as arguments by the Vistas application running on that bridge. The Vistas application can be automatically launched at power on and during boot up, making an instant on type of application. As you can see on this slide, UEI has a bunch of products compatible with this standard. We have proprietary software running on each one of our boxes, and each one of these boxes may look different. They're actually all the same, and we can handle any of the IO and avionic buses listed below. So does this work, you ask? What about latency? That's a great question. During these past months and years, we've been doing tests in order to evaluate the latency involved and introduced by Vistas virtualization. The first one concerns the analog and discrete signals, and the second one, the ARINC 429 bus. For the analog and discrete, a signal generator sends a step to the acquisition bridge. The acquisition bridge acquires a signal and pushes the associated packet in the Vistas format onto the Ethernet bus. The replay bridge receives this Vistas packet and generates the corresponding signal. The signal produced by the generator and the one generated by the replay bridge are simultaneously displayed on the scope, on the oscilloscope. The delay between both can be easily measured, and that would be our latency measurement. Now let's look at ARINC. So we've got a moving inertial sensor that sends its attitude to the acquisition bridge through an ARINC channel and message. The acquisition bridge acquires and timestamps that signal and pushes the associated packet in the Vistas format, again, onto the Ethernet bus. The replay bridge receives the Vistas packet and generates the corresponding ARINC message. The message produced by the replay bridge is also acquired and timestamped by that acquisition bridge. This way, the latency is calculated through the analysis of those packets. And yes, in both cases, it's measured less than 2 milliseconds. Pretty good. So we are working on 1553 as well. Currently, the available MIL standard 1553 implementation is limited to the bus monitor capability. Bus controller and remote terminal capabilities are under development. One of the most complex scenarios to study is the one described here in the slide, a configuration with a real bus controller and some remote terminals, real and virtual, on side A, and then we've got other remote terminals, real and virtual, on side B. We are in the process of ensuring the communication between both sides and evaluating the limitations in such a configuration. The fact that the MIL standard 1553 requires a remote terminal response time between 4 and 12 microseconds makes this scenario very, very challenging. So to address this 1553 latency issue, we are evaluating another transport protocol. You recall that we are using Ethernet UDP currently. Well, we are proposing another candidate called RDMA Rocky version 2 transport protocol. The main benefits of this protocol would be strong latency reduction, could be a few microseconds, significant latency jitter reduction, ultra low CPU overhead, drastic packet loss reduction, the capability to offer light multicast message transfer, efficient usage of existing network architecture, and message routing capability over a wide area network. Rocky version 2 is already largely deployed on existing IT networks on different application domains like cloud computing, enterprise data center servers, big data, and financial service, especially the real-time high-frequency trading business, where a couple microseconds equals lost fortunes. As you can see by this slide, key IT players are involved with this RDMA Rocky protocol. So let's review the difference between Rocky or RDMA and the UDP IP scenarios. So for UDP IP, the packet transfer between the two nodes with the legacy UDP involves different operating system resources and multiple copies of the original data buffer. Over here on the right, with RDMA, the data buffer is directly transferred between the application and the network interface card, minimizing the number of copies data copies, reducing the resources needed. The main targeted benefits of this protocol again are strong latency reduction, again, because we're going straight into the buffer. The lowest latency we've seen is around 1.3 microseconds, significant latency jitter reduction, low CPU overhead, it doesn't have to deal with all those different layers, packet loss reduction, the capability to offer lightweight multicast message transfer, and of course, the efficient usage of existing network infrastructure, and then the message routing capability over a wide area network. And then you can see the graphs on the bottom. Throughput has increased with quite a marked decrease in CPU utilization. The proposed solution is based on version 2 of RDMA over Converged Ethernet. It's commonly called Rocky version 2. There are other implementations of RDMA over Ethernet, for instance, like iWarp, but we've found that Rocky is the one that's most widely deployed. It is compatible with 1, 10, 40, and 10 gigabit copper and fiber Ethernet, and also allows for link redundancy. Rocky version 2 protocol exists on top of either UDP IPv4 or IPv6 protocols. So it could be deployed on existing IT infrastructure and routed onto your wide area network. However, in order to make this technology a lossless technology, it must be implemented in conjunction with these additional 802.1 standards. So BB, or link level flow control mechanism, AZ, or bandwidth reservation, and AU, end-to-end congestion mechanism control. So what we're trying to show here describes what could be a Rocky implementation on our new CPU board in the frame of this Vistas deployment. The card is based on a Xilinx UltraScale chipset, which is composed of a quad-core ARM, a dual-core ARM, as well as a Mali-core up to 66 megahertz, and of course, last but not least, an onboard user-programmable Xilinx FPGA. In this configuration, the ARM cores will be involved for configuration, command and control, while the real-time data transfer will be done without their involvement or involvement of the operating system. So the system will be able to accept a very high number of packets associated with Vistas and will reduce latency to a minimum. So why does this work and how does this help? Since there are no wires and behavior or systems can be virtualized, once a model is defined at the conceptual phase, it can be reused all the way up to the training simulator at the end or anywhere in the middle. It works for local testing of a component or local testing as a hybrid test bench for larger systems. Components can be added in as they are available and virtualized when they are not. And to take this even farther, the components or even the models do not have to be co-located. Remote distributed testing works and is currently used across Europe and the United States. Models are being reused for validation testing and even for the flight trainers of the fully vetted and deployed products. How can this help your design process get off the ground and flying? Well, thank you for your time. Now it's your turn. And we are lucky enough today to be joined by Christian Herpeben, who can be considered the father of Vistas, what we were just talking about. With Chris both this webinar and Vistas itself would not be possible. So I'd love to hear your questions since we have Chris here as well. So Chris, if you're here, one of the questions I see is, can you say a little bit more about the ECIC file?
The ECIC is needed to configure all the addresses and all the network behavior. So when you have the model, you define what in the ECD file, you define what are the input and the output of the different component, but we can reuse different instantiation of the same model. Imagine that you have a two-engine aircraft and you can use the same component for the modelization of the engine. But of course, when you have to implement this, you will affect different addresses in order to make the difference between the right and the left engine. And all this information are described in the ECIC.
Thank you. And then another question was, have there been any studies on Vistas and its successes?
So we have many done in different entities, different proof of concept, and now we are using Vistas in operational mode, but we are still working on the development of the release B that will be available end of Q1 next year. This new release will bring additional functionalities, will introduce the RDMA as mentioned by Eric, and will offer functionality like control on command, pollution mechanism, error injection, monitoring of internal data of the model. So it will be more complete. At the moment, in the Rev A, the focus is on the exchange of information between the different components.
Thanks, Chris. So Shannon, I haven't seen any more questions, have you?
We aren't seeing them on our end, but I know that we have sent that reminder. So attendees with us, go ahead, submit your questions for our speakers today using that Q&A box. And we can give it a couple minutes unless you want to continue any conversation.
Well, Chris, do you have anything to add?
No,
that I may have overlooked or misspoken?
so the key point is the fact that Vistas make life easier. Building a bench is not an easy task. It can take months or even more. Sometimes it's more than 1 year to define all the wiring, drawing, the realization of the wiring, validation of the wiring, and it's sometimes a nightmare. And as mentioned by Eric, the key point for a bench is to be available before the first flight test. Okay, using the Vistas approach give a big opportunity to reduce drastically the cost and the cycle of the bench production. So some studies have demonstrated that we can reduce, using the Vistas approach, the global cost of a bench by 30 to 40%.
That's a great number. Thank you, Chris. Well, Shannon, I'm not seeing any more questions pop up at this time.
Me either. I think you must have covered that information exceptionally well today, that our audience isn't left with questions. You answered them all for them during your presentation. Although it actually looks like we got a question that just came in.
So, cost advantages. First, as mentioned previously, it reduced the building of the bench itself. But it's also a good opportunity to share resources between different bench. Imagine, for example, that you need a weather radar on many benches. This weather radar will not be used 24 hours every day. So using Vistas, it's very easy to share some very expensive resources between benches. This is the second point. The third point, which is for me at least more important than the cost of the bench itself, is the fact that we can start very early the integration test. As mentioned by Eric, you can start your integration with still some component at the manufacturer facilities. It means that it can start earlier, and it means also that the manufacturer has all the resources to be more efficient during the test activity.
Perfect. That's a good answer.
So to be clear, it has a good effect on the building of the bench, but also in terms of usage. You have not to redevelop model along the development cycle. You can reuse exactly the same tools. As mentioned, you don't care if the equipment is the real one or the virtual one. The exchange will be exactly the same. So it means that your display tool, for example, don't need to know if you have if it's a real or virtual equipment. So if you have built a scenario, you can reuse exactly the same scenario with virtual and real equipment. It means that the same scenario will be used during a big part of the development cycle.
Perfect.
All right, well, if there aren't any other questions to ask live, you can see Eric's email written here on the last slide, and you can always reach out to UEI directly. I will leave it to Eric and Chris. Do you have any closing comments to make? We can wrap up if there are no other questions coming in.
I just, again, would like to thank everybody for participating and letting us use some of your time.
Perfect. Well, we would like to echo those sentiments on behalf of AUVSI. We'd like to thank you, Eric, for this excellent presentation, and Christian for your thoughtful answers to the questions that were submitted today. So attendees, just as a reminder, you will receive a link to access the webinar recording within the next week or so. And we'd once again like to thank our sponsor, United Electric Industries, for their generous support of today's webinar. So AUVSI does continue to strive to bring you education through our events and our webinar programming. So just be sure to check in frequently to see what our future offerings are. And if you have any additional questions or comments for our team, you can reach out to us using the email education@auvsi.org. So lastly, today's program is copyrighted by AUVSI with all rights reserved. So thank you all for joining us today, and we hope you have a great rest of your day.
Thank you, Shannon.
Thank you.